Welcome to everybody, both fellows and visitors. It is a delight to be here. For those of you who don't know me, I'm John Aston. I'm the current president of the RSS. And I'm really excited that we're here today to discuss the paper, Some Statistical Aspects of the Covid-19 Response by Simon Wood and his co-authors. We've got a meeting here today, as you are all aware, here actually in the Hallam Conference Centre, but we've also got an online audience. So lots of people joining us online. For those of you who are online, please do keep your microphones muted and your cameras turned off. There will be a recording of the meeting will be posted on the RSS YouTube channel. So if anyone prefers not to be filmed, please do let us know and we can edit that part out. Well, I can't, but somebody can edit that part out. If you experience technical problems online, please use the support chat box and hopefully something will happen. We look forward to hearing the discussion a little later on and have had a really strong response. So thank you for everybody who has said they would like to contribute. So lots and lots of people in advance have said they'd like to talk. This means it's highly unlikely that we'll have much time for people who have not already said they would like to talk. But for those of you who have said you'd like to talk, if you'd like to talk for less than 5 minutes, we would be very grateful. And that means more people can talk. So we will do as much as possible to get as many people to contribute to this as we can. I think there's going to be a really exciting and lively discussion. Of course, if you don't get to talk, there's still absolutely an opportunity for you to contribute. We'd welcome contributions in written form up to 400 words, and these will be published in the journal Series A, along with the paper when it gets published. So the paper today is going to be presented by Simon, who's from the University of Edinburgh, and it will be published in 25-26 in the Journal of the Royal Statistical Society, Series A. So can I now ask Simon to come up, and I'll welcome Simon, please.
Thanks. So I think wherever you stand on this topic, then any discussion of it involves a certain amount of cognitive dissonance, and maybe dissonance is not always such a bad thing. That's Arnold Schoenberg there. So today is actually the fifth anniversary. Oh yes, I'm terribly sorry. And so today's the fifth anniversary of quite a good day in the UK epidemic. It's the fifth anniversary of the day that deaths in the first wave started coming down, and also, at least in England, ICU occupancy and mechanical ventilator use had all peaked. Now that was obviously good, but it wasn't exactly what the policymakers had expected. So if you look at paragraph 182 of Dominic Cummings' evidence to the COVID inquiry, it says this photo shows a hard copy of the actual graph shown to the PM on the 24th of the 3rd, given we'd ditched plan A, i.e. given we'd locked down, peak around the 15th to 20th of April. Okay. Now, in this context, a week's quite a long time, and the discrepancy goes unremarked in Cummings' evidence. But I think it's not the only place where at times the data didn't really quite agree with the COVID models, the policy or the narrative, and that's largely what this paper's talking about. We're not going to discuss why this happened. There's a lot about the psychology of revising your opinion, I think, that comes into that. We're not going to touch that. We're not really going to discuss the consequences. Lots of people have written about that. We're just going to concentrate on some of those discrepancies. Now, one thing that was perhaps over prevalent during COVID itself were a number of false dichotomies, I think, that were posed, which we'd like to try and avoid. There was this kind of false dichotomy between lockdown and do nothing, between being pro-lockdown and being a COVID denier, between protecting the NHS and NHS collapse, between saving life and saving the economy, being for universal vaccination or anti-vax, being pro-SAGE or anti-science, recession versus no recession. They're all false dichotomies. I think there's one dichotomy that is perhaps worth a little bit more thought, though, that's perhaps useful for thinking, and that's about fitting reality to the model versus fitting the model to reality. That is something that's perhaps worth thinking about. But here we'll try and be concerned less with binary absolutes than with degree. So a good example is that life itself, of course, is non-binary, that life's a fantastically multi-dimensional thing. And so if you're thinking about measuring life loss, what unit should you use, right? And there's no perfect answer there, but I think years is a much better unit that tends to align with people's notion of fairness rather than forgetting the units and binarizing. Okay, and just to see that, I mean, if I tell you that by May 2023, COVID had been implicated in deaths of at least 0.1% of the world's population, I could tell you the same thing and say that that's about a life loss of about 3 days per capita. And people tend to react quite differently to those two statements of the same information. Okay, so units actually do matter. Now, I wanted to get onto the paper itself then. So part of what we think was perhaps not so ideal was some exaggeration in the presentation of risk. And this is perhaps the most notorious example from SPI-B advising the government in March 2020. A substantial number of people still do not feel sufficiently personally threatened. It could be that they are reassured by the low death rate in their demographic group. The perceived level of personal threat needs to be increased among those who are complacent using hard-hitting emotional messaging. Okay, now that's quite an unusual approach. You're arguing for distortion. And so the data that gives you kind of an indication of the real risk profile is shown down at the bottom left there. So I've plotted just all deaths in the UK between March 2020, August 21 by 5-year age band. And in black are the COVID deaths. Okay, so you can see, you know, for the young, the risk is pretty low. If you look on the right-hand side, those are the under 45s. And there you can see that not only is their absolute risk not terribly high, but their COVID risk is also really very small in relation to their background risk. Okay, so the quote there is really asking for a distortion of the risk to be used. Now, it certainly worked, this increase in the perceived threat level. This is an article from The Guardian from April, and it's comparing COVID and the Black Death and concluding that in some respects, COVID is actually worse. So I'll just read a bit of it for you. There won't be much economy left once the second wave of infection has finally settled down, because all the top shops will have to be raised to make space for graves. Right? Well, we can compare using data the seriousness of the Black Death, COVID and say influenza. So each one of these little figures here represents a week of expected life loss. If you were unfortunate enough to be around for the Black Death in 1348-9 as black figures, influenza 1918 is in blue. The UK escaped relatively lightly, and red is sort of COVID under and minimal mitigation, right? So these are really not comparable. Now, even more moderate commentators tended to repeat that this was the worst pandemic for a century. So this is a perfectly reasonable article from the New Statesman, but repeating that claim. Now, the WHO puts the HIV/AIDS death rate at about 27 to 48 million. And the expected, the average life loss per victim there is substantially higher than the average life loss was per COVID victim. So I don't think it's sustainable. Now, from mid-2020, one of the things that came to the fore was the risk of long COVID after mild illness. And this was often put forward as a reason for continuing with controls. Now, clearly, long COVID exists, right? Any serious pneumonia is likely to have long-term health consequences. There's going to be knock-on effects. Post-viral syndromes are certainly real, and they're bound to rise with a new virus. But the evidence for an exceptional risk from long COVID, I think, was weak. There was a vague definition of the syndrome itself in most papers. Many papers used non-representative samples of convenience to examine prevalence, lacking control groups, and typically with problems involving low response rate and high and differential dropout. And just to illustrate point one, here's the nice definition of long COVID syndrome: signs and symptoms that developed during or after an infection consistent with COVID-19, continue for more than 12 weeks, and are not explained by an alternative diagnosis. Okay, so that's really post hoc, ergo propter hoc, right? Just waiting to happen. I'm actually going to skip this. There's too much information. It's an example of a good study, but there's too much numerical information and we don't have time. But basically, you can read more of it in the paper, but the more careful studies tended to show pretty low rates of persistent symptoms after mild COVID, apart from loss of smell and taste. They also tended to show that self-reported long COVID occurred at substantially higher rates than those that were definitely associated with COVID itself. But despite that, the public messaging really stressed that, you were at risk from long COVID. Now, again, the fact that there is exaggeration doesn't mean that we're arguing in any sense that there is no problem, right? The ONS data, for example, imply up to 80,000 economically inactive people as a result of long COVID. That's a pretty substantial number. But for comparison, it's about 600,000 people inactive for each of musculoskeletal disorders and mental health disorders. Okay, so you do need to keep it in some perspective. Now, at the same time, some risks, I think, were being exaggerated. Others were being downplayed, and those were in particular the economic risks and the health risks from the economic risks. So early on, the Bank of England, for example, was quite vocal about saying that this is a really huge economic shock, largest for 300 years, apparently. But later on, they kind of got with the programme. So if you look at the right-hand graph, that's just taken from the Bank of England website in 2021, and it illustrates the progress of the quantitative easing programme, essentially funded by money creation that was paying for all of this. And you can see that it looks like a nice steady linear increase, nothing terribly much to worry about here, except that if you look at the x-axis, it's a completely non-linear axis that's being used there. And in fact, what's labelled August 2016 could just as well be labelled January 2020. Okay, so I've redrawn the figure on the left-hand side here, right, and then redrawn with a linear axis the same data on the right-hand side, presenting an entirely different picture of what was going on in terms of that economic hit. Also, just to illustrate that largest shock for 300 years, there's the quarterly GDP change since 2005, showing the financial crisis of 2008 and the COVID-19 lockdowns. Okay, so it was a big hit. Now, discussion of this often involved one of these false dichotomies, saving life versus saving the economy. And to buy into that dichotomy, you really have to ignore a lot of what was known about deprivation and life loss in the UK. So in particular, if you look at the Marmot report 10 years on, which came out early in 2020, well before the pandemic, it documents in a good deal of detail the large UK life loss that is associated with economic deprivation and inequality, and how that life loss increased after 2008 and the subsequent austerity that followed on from it. Okay, now, again, economic shock from COVID, the largest for 300 years, apparently, unclear that our ability to manage that shock has improved since the 2008 crisis. I've extracted from the Marmot report this couple of figures here. And what's plotted on the left-hand side there is life expectancy in years against deprivation decile, area deprivation by decile of the population. Okay, and so blue for men and red for women. There is one data point there that's probably a data error, but I've rechecked the data and the same points are going to hold whatever. Now, the key thing about those curves is you can see the steep slope, and you can see that there's about a decade difference between the most deprived economically and the least deprived economically. Now, if you take the view, as I think is reasonable, that the least deprived are telling you biologically what ought to be possible in terms of life expectancy at the moment, then all those lower life expectancies are effectively avoidable life loss at some level. Right? And if you take the top decile and compare everybody else throughout, that's about 290 million life years of avoidable death, avoidable life loss. If you just take the top half of the range instead, saying, well, we can't achieve the top decile, that's still 140 million life years. So these are big numbers. Now, after 2008 and the consequences of dealing with that, those curves steepened. Okay, they steepened. And basically, the degree of steepening is illustrated on the right-hand plot. And if you total up the extra life loss from the steepening, then you get to about 9 to 12 million life years, depending on exactly how you do it. Now, why do we expect less to happen from the COVID shock than from 2008 austerity? Not clear. For comparison, if you take the worst Imperial College scenarios right at the beginning, and then sort of figure out, well, okay, what might reasonably the measures have saved, that's about 3 million life years from COVID. Okay, so these figures are comparable, right? You need to think about them both, I think. Now, as I said, we don't really like to binarize when talking about life loss, but the discussion often involves things like excess deaths, where binarization is what happens. So we'll talk a little bit about excess deaths now. So, for example, this graphic comes from a University of Glasgow study that attributes 300,000 excess deaths to the austerity that followed on from the 2008 crisis. Now, how do we work out excess deaths? Well, we work out first the expected deaths if things stay the same as over the preceding 3 to 5 year reference period. So that's typically what's done. And then your excess deaths is simply your actual deaths minus your expected deaths. Okay. Now, the question, of course, is which things should stay the same, right? Conventionally, it's deaths by week of the year, perhaps with some statistical trend adjustment, but that's basically what you're doing. Now, that doesn't account for population aging, and we have an aging population. So we argue in the paper that really it's age-specific per capita death rates, i.e. life tables, that are the things that you should keep constant from the reference period, and you should use those, just iterate the aging and death process forward in time. And that's what we've done on this plot. So if you look at the left-hand plot, the black dots are actual deaths by week of the year, right? And the blue curve and the expected deaths that we get by iterating these life tables that were computed using 2017 to 2019 data. Okay, so we start with the age structure at the beginning of 2017 and iterate this aging and death process forward in time. There's a seasonal adjustment, but we don't need to worry about that here. So if you do that until 2019, the total and the expected match to within 50 deaths. So we've got this right. Okay, so we can go on from 2020 and just see what we expect to happen from 2020 onwards, and that's the continuing blue curve, right? So then you subtract the expected from the observed deaths, and we can work out the cumulative expected deaths, and that's the red curve on the right-hand side, okay? And that comes up with about 95,000, I've said 90,000, it should be 95,000 excess deaths until the end of 2022, okay? And that's quite a bit less than, say, the ONS figures that are more like 160-something thousand. Okay, so it's really quite a big effect, this aging effect. Just as background, there are about 640,000 deaths in the UK per year, and that sort of 95,000 is about 20% above the excess deaths from the 68-69 flu pandemic on a per capita basis. Now, does aging really make that much difference? Right? There's been quite a lot of resistance to this, but a very simple plot illustrates that, yes, indeed, it does. So on the left-hand side, what I've plotted in blue is the age structure of the UK population, the number of people in each 1 year age class from age 50 upwards, from the high mortality classes upwards. So I've done that for 2017, and I've done it in red for 2020. And then I've coloured the differences, right? So any pink difference is an increase in the population in that age class. Any blue difference is a decrease. And then we can simply multiply the differences in population between those 2017 and 2020 by the per capita death rate expected in that class and just accumulate them across the ages. And that's what's done on the right-hand side. Okay, and when you do that, you can see that you're getting 30,000 extra deaths expected every year just as a result of that population aging between 2017 and 2020. Okay, so it's a real effect. Now, there are other data, I think, that played a surprising part, perhaps, in the management of the response, and certainly the presentation of COVID. One of those things with the case data, and this was always puzzling to me in the UK, where you had proper measurement going on of the prevalence of COVID. Case data were typically treated as if they sampling measurements. So that's the black and the blue curve. And I've lined them up, I've scaled them so they match just over the middle range of the data. And what you can see with the case data is this tendency. Right. Is this tendency for the cases to accelerate on the upswing much more rapidly than prevalence is really doing. Now, another strange thing, which is cropped off the bottom of the slide, is the R number is closely related to the rate of change of number infected. And a really odd argument was often made that actually the case data are reliable for estimating the R number, provided you look over a short enough period of time, right? And that appears to be equivalent to saying, well, if we look over a short enough period of time, the bit of the derivative we don't like is going to disappear. Now, this isn't just nitpicking, right? Here's a paper from BMC Medicine 2021, the impact of non-pharmaceutical interventions on SARS-CoV-2 transmission across 130 countries and territories. So sorry, it's a terribly small font, but basically things like school closures, workshop closing, cancellation of public events. They looked at the effect supposedly of all of those on the R number, and they all appear to depress it, right? But look at contact tracing on the end there, okay? So contact tracing apparently increases the R number. How was the R number calculated, it was calculated from the case data, right? I mean, the contact tracing is going to increase the number of cases, right? This is a serious problem. But cases were highly correlated with prevalence. People will say, well, yeah, the R numbers were quite high, the R squares were quite high. So here's ONS prevalence against cases in England, plotted in time order. And you can see these systematic changes in the correlation that's going on through time. It's not random correlation, right? This is systematic variability. You can plot against incidents, the middle plot, the same kind of thing happening. And Scotland, complete disaster on the right. So let's talk a bit more about kind of following the science. This is my favourite cartoon from the entire pandemic, indicating perhaps that government advisors may have their own pressures operating on them. So just following the slightly lighter theme, so following the science fomites. So these are two pictures from near Edinburgh. So one's in Edinburgh. It's a pedestrian crossing and it's been disabled, so you can't press the button and risk COVID, right? On the right-hand side, there's a bunch of portaloos in a forest car park, and every other one has been closed. Now, if fomites are a massive problem, right, then the left-hand side there makes perfect sense. The right-hand side, on the other, is doubling your risk. All right, if fomites are no problem, well, the left is completely pointless. The right might sort of make sense, except you're outdoors. Here's more following the science in Scotland. This was Scottish government advice on face masks. Scientific evidence and clinical and public health advice is clear that face coverings are an important part of stopping the spread of the coronavirus. To their credit, they gave a link to the evidence that was supposedly clear. Well, here's what it said. Wearing a mask may slightly reduce the odds of primary infection with influenza-like illness by around 6 to 15%. This was low quality evidence. Right? I don't think this increases public trust in science, doing this sort of thing. So the epidemic models were the other place in which we were more seriously following the science. Right? We were, locked down for months as a result of these. So most of these were based on this kind of 100-year-old idea of SEIR models. Right? So your population starts out with most people in a susceptible compartment. They transit to an exposed compartment on infection. Then at some rate, they translate to an infectious compartment where they may infect other people, and then they recover or in some cases die, of course. And there's linear flow between those compartments with a non-linear flow from susceptible to exposed, which is proportional to the number of people infectious. Okay, so just to give you a little illustration then of what those look like, here's just a little animation showing how that works if you sort of implement it as an ODE or if you implement it as a stochastic simulation. And you can see, pretty much the same dynamics in all cases. The susceptibles decline, recovereds increase, and you have these waves moving through the exposed and the infectious population. Now, I think the real objection to this kind of simple model is the way in which it treats everybody as clones. Right? So we're treated completely clonally within these models. We're all identical. And in fact, we're all identical and behave like ideal molecules of an ideal gas in a box in the way that we mix. And of course, people are much more heterogeneous than that. And I think not going to work. And that has consequences. It has consequences on the dynamics of these things. So what I've done is to illustrate this with just a little simulation. So each of the blue dots on the left-hand side represents a person who's susceptible, and the red dots are infected people. And they're all identical. So they've all got equal probability of making contact with anybody else on a day. And if one of them is infectious, you'll get an infection event. On the right-hand side, I've made some of the people much more sociable than the others, and they're much more likely to meet other people. But I've set both simulations up so that the average number of contacts per day is identical in both cases. Okay, and so I've got the average R0 is identical. Okay, so we can set the simulation off. Well, I could if I could operate this. So the sort of thing that happens is, a day happens, we get some random contacts made. Some of those will cause infections. If we run this a couple of times, you'll see that obviously the more socially connected people are more likely to make contact, more likely to get infected, and so on. And of course, if you continue running this through time, it's socially connected people. So that in the homogeneous population, in the homogeneous population, we then end up with epidemic that goes on longer, there's a higher peak, and more people cumulatively affected. Now, I didn't cook that simulation. I mean, it's a general property of these systems. You can kind of summarize it in a graph something like this. We can summarize the degree of connectivity in this thing I've called the unity coefficient, where 1 would be complete clonal behavior, everybody's identical, and 5 is much more heterogeneous. And the final proportion of people who end up infected will depend on that immunity coefficient and the R0. Okay, so R0, 2 will be shown in red, and then we go on. And you can also attempt to estimate what that immunity coefficient might be. In the UK, estimates came out as about 3. In the US, around 4. US Sydney, about 4.5. So they're fairly high, these things. And okay, is that better? Yeah. Oh, okay, I'll continue. But you can see that this is actually a fairly major effect. If you neglect this, you are going to overestimate the size of these infectious waves. Now, there were other modelling emissions, of course. Hospital-acquired COVID is an important one, was known to be a big problem from Wuhan and from Lombardy. This was published as a big problem. If you're primarily interested in avoiding health system overload, it's obviously a big problem to leave it out of the models. Another interesting emission, at least in many of the analysis models, was the split of the population into low R lockdown compartments and high R key worker compartments. Now, that's a problem because R is basically the average new infection per infection, where the average is taken over the infections, right? Now, over time, the proportion of infections is going to move to most of the infections are going to end up in the high R compartment, right? And so you're taking an average over infections which are mostly in the high R compartment. So after lockdown, what you expect to see is a dip and then a recovery. So you better have that in the model. Seasonal weather effects were omitted largely. Non-mandated behavioural changes simply weren't in there. And of course, the negative consequences, the interventions were not there. But I think that the most significant omission was that these models were not really validated in advance for predicting things about interventions of the magnitude that were being made. Now, there was hints early on that this might be a problem. For example, Imperial College Report 12 made projections for all sorts of countries across the world about what would happen under different social distancing scenarios, right? Different NPIs. Now, for Sweden, they projected about 35,000 first wave deaths for the policy most like Sweden's, and 6,000 actually occurred. Okay, so that's quite a mismatch in this context. Of course, by December 2021, we then got a much more dramatic example, or an equally dramatic example. SPI-M predicted or projected serious problems in the face of Omicron if the UK did not lock down, essentially, but the UK didn't lock down. So again, you can compare the projections in colour on this plot to reality, which is in black, and there's again quite a mismatch. Now, to be fair, the Warwick is in blue and the London School are in orange there. The Warwick scenarios did include one that got close to reality, but I think it's fair to say it wasn't one that was presented as being a serious possibility. And so I think really this emphasizes that unvalidated model predictions are mathematicalized opinions. That brings me on to lockdowns. So we locked down in the UK on the 24th of March 2020, and fairly soon thereafter, reconstructions of incidents started being published, like this one on the left from Imperial. Now, they seemed slightly not quite right to me, partly because of things like this photo in the middle. Now, I took that photo at rush hour at Bristol Temple Mead Station on the London-bound platform on the 16th of March 2020, right? I mean, it's empty. And it didn't normally look like that, right? The right-hand plot would be more like what it usually looked like, okay? People's behaviour had changed quite dramatically. It seemed implausible to me that you could really have exponential growth up until lockdown. Now, that was sort of pre-hoc, if you like. Post-hoc, I think a lot of people sort of buy into the following argument, that all over the world, cases and deaths were increasing, then governments locked down, and then cases and deaths declined. So lockdowns must have done it, right? And I think that's a fallacious argument, because no government was going to lock down if the cases were not increasing, and cases and deaths were going to come down eventually. So
increased lockdown decrease as a pattern was inevitable, right? It contains no information. What you need to know is what were daily new infections doing. Okay. Now, recorded cases, I think, are kind of useless for trying to work this out. They're really just not good enough early on. But daily deaths and time to death data are more reliable, at least post hoc, and we can try to use those. So it's interesting to look at what happens if you try and do that. So here's what information was available on the time from symptoms to death and infection to death for fatal COVID cases. So I've summarised on this plot the results from 5 studies available in 2020. Veterinary, Wu and Linton are all early studies. They're pretty small sample sizes, but they're correctly controlled for right truncation. And they're, fairly similar patterns coming out of them. The chest one I won't talk about here. Isaric is from later. That was from August 2020, and that's 24,000 patients. That one's based on the one in black. So it's the one that I'll use here. Now, the infection to first symptoms distribution, there were quite a lot of studies about that, and there's a McKeigue meta-analysis in 2020. So you can fold in those together, and you get a model, a log normal model. Seems reasonably okay for that. So our infection to death model could just be a simple convolution model. So let's have F as log of incidence, log of new infections per day. We'll have FW being a cyclic function of day of the week, just to take into account that kind of health service wobble that happens in the UK. And then our expected deaths on day I will be given by this simple convolution model. So the exp of FW is just that sort of wiggle. And the important thing is the summation. What we're doing is to sum over incidence, new infections per day, at day I minus delay D, and we're going to multiply that by the probability of a fatal disease of duration D. That's our pi D thing. So the pi is from the plot on the previous page. All right. We'll have deaths as negative binomial, and we'll have FW and F assumed to be smooth splines or something like that. Now, that's almost a sort of generalized additive model structure, not quite, but we can use a very similar empirical Bayes approach to estimate the model and the smoothing of its components. All right. So if we do that, here's reconstructions using the ONS data on the top. So daily deaths from the ONS. So on the right-hand side, the blue points are deaths per day from the ONS. And on the left, you've got incidence reconstructed with all the uncertainty in the distribution. The distribution of distributions all kind of folded in. You can see that we appear to have an incidence peaking before lockdown. And that blue bar chart is showing you the posterior distribution of the day of the peak. Now, you can argue that the ONS data are not great for this purpose if you're interested in community infections, because they include care homes. There's quite separate dynamics going on there. So in the middle, we've got UK hospital death data, daily death data, and the deconvolution applied to those. And that's perhaps the one that should be taken more seriously. At the bottom is the data for Sweden. Okay, and so Sweden didn't lock down, of course, famously. And you can see that the turnaround in incidence appears to be almost at the same time. But what you get, which you didn't get with lockdown, is then that kind of subsidiary peak later on. Now, once you've estimated incidence, you can plug incidence into an SEIR, if you like, solve for the number of infectious, and actually compute your R number. So that's been done on the left-hand side there, again with the uncertainty folded in. It's the log of R that's been plotted there, and you can see that appears to be below 0 before lockdown as a sensitivity analysis on the right. Now, this was frustrating. We did this work in May 2020. And basically, referees withheld peer-reviewed status until March 2021 without ever questioning that the method, the data, or the conclusion was actually wrong. By that time, there was lots more data available. So this is for the entire pandemic run. And you can see the 3 lockdowns by that time as red vertical lines. Now, there's some quite interesting other data arrived from that. There's the REACT-2 study. There's a proper randomized study in which people were tested for antibodies. And then the genius thing was that the people who tested positive were asked when their symptoms started. So it's imperfect, but you can reconstruct the epidemic that way. You have to lag from time from infection to first symptoms, of course. And that's what's been done on the plot, but that's the blue jagged curve there, and it's showing a similar kind of a pattern. The black dots with the uncertainty bands, that's what comes out of the ONS proper randomized survey. That's their incidence reconstruction, and that's also doing the same thing. These peaks in the incidence profiles before the lockdowns, the R numbers below. Because that appears to be relatively relatively reliable, we applied the same thing to across all the European countries where we could get data. You see rather similar patterns occurring again and again, but I think the kind of interesting ones, the really interesting ones, are Sweden and Switzerland. So Sweden, you know, we all know, didn't lock down, and you get wider peaks. You get these subsidiary things going on, but you don't get a complete explosion. Switzerland's interesting because they locked down hard first time round and then stayed much more open than their neighbours after that, and you get a similar looking second wave to what goes on in Sweden. Now, there were a lot of alternative narratives about this that were basically based on fitting population dynamic models, and they all said that incidence was surging up until lockdown. And we looked at several published ones and tried to figure out what was going on. So the MRC Biostatistics unit fitted a population dynamic model, but using basically the same time to death distribution as we did. The model was controlled by allowing contact rate modifiers to change on a weekly basis after lockdown, but there was no change before lockdown, at least in the published version that we found. And of course, that means you've built surging incidence into the model. Flaxman et al., the famous Nature paper, they also used a dynamic model, a renewal model in this case. They allowed the R number to change every time the government said that the NPI should change. Okay, so a bunch of step changes. But that also meant that the R number couldn't change after lockdown. So we can't get the dip in recovery that we expect, and we do see in the Birrell paper, and that has interesting consequences. So we tried relaxing the assumption on R, just letting R vary as a spline, and then you get back to results like ours. Much more complicated model came from Imperial College, report 41 in December 2020. They fitted to 19 5-year age classes, a model with this complicated structure shown here, where you've got all sorts of health service compartments involved so that they could fit to all sorts of health service data streams. But they controlled the R number again with a simple piecewise linear multiplier on contact rates. And again, we think that was too restrictive. When you put in something more flexible, you get back to results like ours. So we think that the alternative narratives were really built into the R models, that the MRC essentially built surging incidence into its assumptions, at least in what we found published. In the case of the Imperial models, as both of them shown here, both Flaxman and the report 41, basically, if we relax the strong assumptions on R, then that's what we get. Okay, so it's the same model structure otherwise. Similarly, for report 41, if we relax the strong assumptions controlling R, we get that. Okay, so we can put everything together on one plot, and essentially this is what we get. Okay, so I'm being told to stop, so I'm going to have to accelerate. So most of what I've told you is things that we thought you could really say at the time, albeit massively strengthened by hindsight, right? But there's some genuine hindsight as well. So do you remember All in It Together, right? We were all told that. Well, between their pre-pandemic high and March 2021, the world's billionaires gained about 1.15 trillion in wealth. That's about 10%. Okay. Now, according to the International Labour Organization, by 2022, Labour's share of income had dropped by about 0.63 trillion from its pre-pandemic, pretty much steady state for the previous decade. So really the signs of building back better seem rather limited from that perspective. And some more health economics insight, right? I mean, we were talked about decreases in life expectancy. Well, here's from the Institute and Faculty of Actuaries. Mortality in 2024 for ages 20 to 44 was materially higher than before the pandemic. Their continuous mortality investigation, which is used to set annuity rates and, you know, determine pension liabilities and so on, that discounts the 2020 and 2021 pandemic data, right? I mean, they deal with it properly. This isn't reflecting those data. Between the start of 2020 and 2024, life expectancy at 65 had dropped by 0.6 and 0.7 years for women and men. So that's what they're projecting going forward, right, for pension calculations. So that in itself, just for that population, is a life loss of 10 million years for the UK. Right, these are substantial numbers. So I think our collateral life loss lower bounds shown earlier were probably overcautious in retrospect. Those were going to be my closing remarks, but I've been told to stop.
So we've got three invited discussants. And so the first one I'd like to call on is Peter Goldblatt from UCL.
Thanks very much. This is an interesting paper, but I think it's a paper in three halves, or 3/3. The first third being largely an attack on others, where the evidence is either weaker or not argued in a way that accepts other views, but is principally to defend the author's position. The second half is much of the statistical analysis, which I could have some comments on, but I'll leave because I think it's largely very good. And the third part is the discussion, which very much accuses everyone else of doing what they had done in the first third, of not providing well-argued evidence. To do this, I'm just going to pick on a few examples where I'm more familiar with the analyses. So the first was the argument that Marmot 2020 showed the effects of the financial crisis. In fact, there is not a single mention of the financial crisis in the entire 200-page volume. What this graph shows is similar to what was shown at the end of that presentation, which is the accumulation of household wealth. And that began in after 2010-12, when the most affluent 10% increased their wealth, while the lowest 30% had no increase in wealth during the years of the coalition government. And that's not coincidental, because in the early years of the coalition government, ministers made a decision to change the allocation formulas to local and health authorities. And this is the NAO data on the reduction in funding. And it shows that areas with the lowest life expectancy in 2010-12 had the greatest cuts in funding by 2019-20. In other words, those who were already illest suffered the worst cuts in their funding. So it was very much a political decision as to who would gain and who would lose over those years. It had nothing to do with the financial crisis, that inequality. And similar to some of the analysis that was shown in the paper, we did an analysis showing the excess deaths in each deprivation decile, showing that they were greatest in the lowest decile and compared to the least deprived. And when you look at the ONS data, it showed that the death rates among the least deprived didn't necessarily continue on the same trajectory as we'd seen in the previous decade, which was a very rapid increase, but they increased much faster than in the most deprived. And in fact, in females in the most deprived decile, they actually decreased. So these were conscious decisions of ministers. They were not directly resulting from the financial crisis. Second point I want to raise is linked to when deaths occurred. And as was commented, the epidemic in care homes was very different to that in the rest of the community. And in fact, that epidemic started largely after lockdown. And it was, according to some that I've spoken to, was a result of agency workers going round the different care homes and transmitting the virus. Now, those agency workers could not have done that if they hadn't been infected post-lockdown. And they, of course, were in the community because they were exempt from lockdown. So it illustrates that perhaps lockdown did have an effect. What could be argued, I think, is that had lockdown occurred earlier, and the authors have argued that no government would have done that, but there were pressures on them to do it, then it would have been at a different point in the curve. A second point in the paper, which I think was touched on differently in the presentation, was about susceptibility. And much of the infection rates and death were not so much about individual susceptibility, though obviously in any infection that is the case, but very clearly related to the proximity of the occupation to customers, and care workers and nurses, the NHS and bus drivers all had much closer contact, particularly in the wild stage of the epidemic, than others. So they were the ones who were most likely to be infected and most likely, given their socioeconomic position, to die. And we can see from this analysis by Ayub Khani that post-lockdown death, the relative rates in ethnic communities decreased where they'd had increases before, and that can again be connected to the occupations of ethnic groups, but other factors have been identified in his and Nafalyan's analysis relating to the risk factors in ethnic groups. Now, the next point I want to raise is that, again, in the paper, it said no one during the pandemic took account of the likely risk of containment measures. This is a model that we developed for WHO, which showed how inequalities would be a consequence both of the direct impact of COVID and of the containment measures. And the purpose of that was to give advice to countries across the world to minimize the effect of both the infection and the containment measures. And just to, again, point to the fact that the long-term effects were socioeconomically distributed of the lockdown measures. And that, again, was a result of policy around not providing support to those most deprived rather than across the board. And what happened there was that the least deprived had their own means, the families had their own means, the most deprived did not and needed more support, whereas the support was universal rather than targeted. And, sorry, quickly go over these. I'll leave that one. There is also the issue of the authors called on everyone to use more data about individuals and their risk factors. This paper, which by Baostab et al., used data on comorbidity and on socioeconomic factors among the 63 million people in the population. And again, what it shows is that mortality continued long after the first 4 weeks of testing positive for COVID, and that the risks were related to vaccine adherence. Rather than the statements in the paper which talked about effects being just over weeks after the infection. And in terms of the age structure, again, this paper shows that survival in median years varied considerably by age. If you take that into account, the displacement effect, which is rejected in the paper, then you see that the excess deaths do increase progressively. They're not just a short-term effect of a few weeks. Thank you.
Thank you. Our next invited discussant is Sheila Bird from the University of Cambridge.
So my career as a biostatistician has spanned 5 decades of epidemics, mostly, however, batting for the Medical Research Council and specifically the MRC Biostatistics Unit, where I'm now Programme Leader Emerita, but also a foot in the other camp, having an honorary professorship in the College of Medicine and Veterinary Medicine at Edinburgh University. So to comments properly, the authors present useful international evidence, mainly modelled, on people's response ahead of lockdowns. But the Royal Statistical Society's COVID-19 task force was concerned that test, trace and isolate instructed close contacts of index cases to quarantine for 14 days without their learning efficiently about how soon during that period of quarantine the contacts tested positive for SARS-CoV-2, contacts of 2 types: A, those who lived in the household of the index case, and B, external close contacts. Also not finding out about actual adherence to quarantine, influential covariates for transmission of the infection and for breaching quarantine. Hence, in July 2020, the Royal Statistical Society's COVID-19 task force recommended 2 key statistical methods to learn efficiently about test, trace and isolate. The first of those was to select a running random sample of households of type A, household of index case, type B, external close contact. Each of those sampled households to be visited on 2 randomly sampled days during the intended 14-day period of quarantine. For example, the first visit on days 1 to 5, the second days 6 to 14. And at that visit, close contacts would be tested for PCR tested for SARS-CoV-2, adherence to quarantine would be observed, and limited covariates noted. In addition, because it was likely that test, trace and isolate would be delayed in reaching contacts, an important covariate was the elapsed time before the contact was actually reached by TTI. Now, I suggested that the field force of the Office for National Statistics Community Infection Survey could efficiently deliver these visits, a suggestion that ministers did not take up. Instead, the quarantine period in the United Kingdom was progressively reduced from 14 through 10 to 7 days on a non-experimental and probably delayed basis. So next time, from the outset, we should adopt the Royal Statistical Society's 2 key statistical methods for gleaning intelligence from TTI lookalikes. The second method was record linkage between contacts and those and the SARS-2 positive PCR diagnoses. And that was done by October 2020, but it took much longer before the information was brought into the public domain. Now, tonight, the Wood team suggest NICE's £30,000 per QALY as a threshold for a nation's outlay when confronted by pandemic uncertainty. And in the main talk, you heard how early modelling had suggested around 500,000 lives lost in the United Kingdom to SARS-CoV-2. In fact, COVID-related deaths, mostly elderly, would be counted as 10 life years lost, and they came in at around 200,000. And so the nation's outlay, in essence, saved, in inverted commas, 300,000, prevented 300,000 COVID deaths, each of them counted as 10 life years, not actually QALYs. So about 3 million life years were gained, as it were, by the nation's outlay on COVID. But the authors point out that that was at a cost which was roughly 10 times the NICE threshold. Now, I would suggest that peacetime thresholds are not the correct reference for pandemics, although an empirical multiplier of the type that the authors have presented could be helpful. However, Wood et al. Offer us just a single UK multiplier for a multiplier of 10 for SARS-CoV-2. Now, as those of us who are statisticians here will know, n equals 1 is statistician's hell. And decision makers really need a distribution of multipliers. Unfortunately, the authors did not provide or apply their reasoning to HIV/AIDS or to opioid-related deaths, which I regard as the forgotten epidemic, because in Scotland, in the 5 years 2006 to 2010, there were 1,970 opioid-related deaths versus 1,864 in the 30 years of HIV/AIDS from 1983 to 2012. Prion diseases, BSE, variant CJD, and also swine flu, a mild thing. Swine flu claimed about 500 lives in the United Kingdom, variant CJD, fewer than 240 internationally. But pandemics, like wars, demand exceptional outlay. See, for example, the long shot on UK Vaccines Task Force. Let me turn now to the presentation of risk and indeed the paper's example from the Bank of England's presentation of quantitative easing was egregious, and a warning always to beware of distortions of time axes and also their mislabeling. Now, during SARS-CoV-2, presentation of a serious adverse event known as cerebral venous sinus thromboembolism with low platelet count, abbreviated to CVST, was associated with the Oxford AstraZeneca vaccine. And the presentation of risk was initially inhibited in two important respects. First, the actual counts of yellow card reports by age group were not put into the public domain, nor the estimated number by age group who had received the Oxford AstraZeneca vaccine. And secondly, the ultimate comparator was not against those who were unvaccinated, who would have experienced risks in the final column. The actual comparator for the United Kingdom was receiving a messenger RNA vaccine. And so immediately I alerted my goddaughter, then in her 30s, not to have the Oxford AstraZeneca, to have a messenger RNA vaccine. And indeed, within a month, the UK's at-risk threshold had been altered to include 30 to 39-year-olds. We've heard impressively about the post-war baby boom and how short-circuiting calculation of expected deaths leads to important error. And that is an important, I think, contribution of today's paper. The ONS is itself working on the statistical underpinning of its work on expected deaths, and I hope they will eschew the emotive term excess deaths. It is also important to distinguish expected deaths calculated by death occurrence week versus death registration week. The UK's first COVID-19 death occurred on the 31st of January 2020, 12 weeks before April, not 7, but it was not registered as such until September 2020, when the family had asked for the autopsy findings to be reviewed. Now, as you will know, since swine flu, the Royal Statistical Society has been calling for legislation to end the late registration of fact of death in England, Wales, and Northern Ireland, where coroner-referred and inquest deaths are not registered until the inquest has determined the cause of death. In Scotland, for all deaths, fact of death is registered within 8 days of death having been ascertained. And so, Sir John, I appeal again to the National Statistician, Chief Medical Officers, Chief Coroner, UK Statistics Authority, Government's Chief Scientific Advisor, ministers and their scientific advisors to legislate for prompt registration of fact of death in England, Wales, and Northern Ireland, as in Scotland, and for this to be enacted for England within 18 months before the new health data research service comes into play. Thank you very much.
First of all, thank you very much to the RSS for inviting me to contribute to this discussion and give me the opportunity to have a debate on some of the statistical and non-statistical aspects of the UK response to the pandemic. Before I start, let me make a couple of declarations about possible conflict of interest. Whatever I say is from my personal opinion as a scientist, as a statistician, and not a member of the SPIM. This is being quoted a lot. It stands for Scientific Pandemic Influenza Advisory Committee Subgroup on Modelling, or on my position at the UKHSA, the UK Health Security Agency. Okay, let me start on the paper. I'll make some generic comments before going into and introducing the discussion on the alternative lockdown scenario. This paper is very much a retrospective and I would say selective journey through a unique situation in the history of this country where scientific evidence had to be produced under unprecedented pressure. We literally had only hours to use messy and contradictory data to shed light in a fog. We should keep in mind that decision would have been taken anyway without quantitative input otherwise. As a statistician, of course, we would have liked to have the luxury that we usually have, and we teach our students to carefully consider model choice, validation, uncertainty. Well, there wasn't any time for any of this. The situation was unfolding very rapidly in an unclear way, scary. In fact, the data from China were sparse. They were not really sharing it. And the pandemic in Italy was precipitating with quite terrifying messages and images, I would say. And we had to do what we had to do in the best of our ability with the data that were available. And it's important that this is not forgotten because this is not at all acknowledged in the paper. In retrospect, obviously, we can have a healthy and interesting, productive, maybe, debate about this statistical aspect. It's not so easy, I would say, to have a productive debate about the conduct of politicians or the media, although, you know, some interaction I had with some journalists, and in fact, the Science Media Center were quite something really excellent, I should say. So I limit my discussion to the data and statistical and modeling aspect of the work. My stance is that there is still lack of clarity on what happened 5 years ago, and I would not necessarily agree with Simon's statement that he made in his interview, that we can say that what we can say can be said with more certainty now than it could be early on. Well, this might be true for some aspects, but not all of them, and definitely not the lockdowns. So together with other colleagues throughout today, I'm going to give examples of this, and I will focus on the first lockdown mainly. So I'll make general comments, and then I'll come to the introducing the discussion on the alternative lockdown narrative. Let me start with the data. I agree with you that about the data on the COVID cases. It was an accounting exercise, I'm afraid, rather than a careful epidemiological data collection. If we had carried this out as a careful design data collection, information on symptoms on scent would have been collected, together with information on the reasons for testing. So such data would have led us to be able to disentangle the signal from the noise which was resulting from the spatially and time-varying opportunistic testing, as well as from the fluctuation due to the test availability. Systematically collected data of this type are usually fantastically informative, particularly if we can correct for the inevitable reporting delay. There is lots of methodology for that. But this was not the case for the COVID data, the case data, even with the data, the delay correction. We tried to make sense of this data, but it wasn't very easy. And so we didn't use them. I also would agree with you that these are incidence data. These are not prevalent data. So it's really not quite meaningful to compare it with the ONS information. Going on to the ONS, I think the authors are a bit unfair toward the ONS. It took time to be set up. It was a very logistical, very complex, but it was a unique resource to the UK the other countries are still envious of. I would like to believe, like the authors, that the availability of a CIS-type stream of data would address all the data requirements. However, at the moment I'm reanalyzing it, and it's not so simple, it's not really so straightforward. One immediate complication, for instance, is access to the data through the research environment, which is secured, which sort of delays access, but particularly delays analysis and retrieval of results. But the authors talk about the need for publicly available data. It's important to bear in mind that the ONS has the obligation to protect privacy. Let me move on to the modeling omission lockdown section of the paper. The authors said the retrospective belief that the lockdown were necessarily ... seems to be based on informal reasoning and a priori modeling rather than data. First, I found this confusing, as they call data the information provided by the retrospective estimates of current incidents. This estimation needs to be done very carefully, and I've got lots of questions. Why estimated fatal incidents, for example? Would 2020 and 2021 touch on this? But in this discussion paper, no alternative estimates of incidents are provided. Estimates of the time-varying probability of dying in hospital? No, I don't want slides. I'll change. Thank you. It's not the right time. So the estimates of the time-varying probability of dying in hospital are now available, have been available for a while, and could have been used to estimate incidents in the population rather than incidents in those who die. This would in practice amount to scaling the deaths that would et al. Use, but the inverse of the probability of dying in hospital, given infection. And this probability changed over time, for instance, due to improved treatment plus to the fact that an increasing fraction of people die at home instead of in hospital. So, and this probability was reduced in this case. So the deaths would have been scaled up by a larger fact after the lockdown, which might have pushed the estimated peak incidence to a later time. Again, Bund 2021 mentions this point, but has chosen not to highlight in the current discussion paper. This incidence would have been much more meaningful. This population incidence or estimate of population incidence might have been much more meaningful as a comparison to the incidence that has been derived from the REACT-2, which might suffer from recall bias, by the way. Second, the second point I want to make is trends in current infection are not the only quantitative relevance. What was important was the impact of this infection on the health systems. I hope Professor Fong later on will illustrate the situation at the time in the NHS. Third, and this is a question, though incidence estimates could be in principle used as a retrospective assessment, they were not available prospectively at the point where the decision on the lockdown needed to be made. At the time of the first lockdown, we only had, and now I can show you, this type of information, short time series, in this case, the number of all deaths growing rapidly over time. Okay, this is all we had, short time series. I wonder, what else, apart from the trends in observed data, deaths or other measure of burden, which are lagged indicator and maybe even affected by reporting data, could be then used for decisions? You mentioned the CIS, but the COS was not available. Let me just very briefly, before they shut me up, introduce the discussion on the alternative lockdown narrative. I would just want to remind people about our model, the model that we, the MSc biostatistics model. This is a SIR type model of the type that Simon described earlier. There is obviously a latent infection process, which is the stage process, and then we have the deaths, which are the results of this process, together with the probability of dying. This is the probability I was talking about before. So here, this lambda is the region and time-specific rate at which the susceptible acquire infection, depends on the content, depends on the susceptibility of the population, and this beta is what measures the external, I've been told to hurry up, an observed temporal fluctuation in transmission. And this is the sort of part of the model has been criticized. That was Bureau 2021. Since then, we've done more work, more recently, sort of introducing all sorts of other data, but more importantly, this new paper, which is in a repository and hopefully will appear soon, which actually looks at a sort of an extension of the original model, making the changes that you were talking about. And these are the results in terms of the RT. Okay, these are three papers, three results from three different models. The first one is the original model, as in Bureau 2021. And these are two models that we've been exploring, where the famous beta parameters has been allowed to change before the lockdown. And this is another model which allows that to change over time, but at the same time introduces more sort of detailed information about the content. Well, the bottom line is these two models. You can see, I mean, this is what you criticized, and the R does change and actually decreases over time before the lockdown, but it stays much higher than one, which means the incidence is still increasing. This is obviously depends on the region. There is a regional heterogeneity in the estimates of the RT, and with London in blue here, experiencing the sharpest decrease in transmission. So you can see that this is the northeast. Yes, there was a drop before the lockdown, okay? So the incidence, which corresponds to these three different models, it's a bit different, but not substantially different. It still displays the same pattern, and this is a comparison with the scaled wound fatal incidence result. So the question is why there is still why there is this difference, and Paul Biro later on will investigate this in much detail. Thank you.
Well, so we've heard from the presenters and the discussants, and we thank them all for their very insightful talks. As is the tradition of the Society, please let's mark it again by giving them all a round of applause. We now move on to the open discussion session. And we, as I said earlier, we've had a really, really strong response for people who'd like to comment on the paper, and those who've registered an interest will be called upon first. It does say if there's time enough for others, you're most welcome to comment. I suspect that's not going to be the case, I'm afraid. So the first person who's registered an interest is Gabriella Gomes from the University of Strathclyde. Gabriella. And oh, can I say again, 5 minutes at most, please. And if you can go under 5, that would be really appreciated.
Okay, so so it's a pleasure to be here contributing to this discussion. So I'm doing this on behalf of my collaborators Ibrahim Mohamed and Chris Robertson, as well as myself from the University of Strathclyde. So I'm just focusing on the mathematical models and on the dynamic models. So this is the model as presented in Simon Wood et al.'s paper, and this is just an SEIR model, but it has this. Is this a point? I don't know. Can I point? Sorry. So there is this lambda. The lambda is the accounts for heterogeneity, person-to-person heterogeneity. And it is another interpretation for it is 1 plus the coefficient of variation of the individual-to-individual variation in susceptibility. And so these models were discussed early in the pandemic, but as the paper says, they were not really adopted due to convictions that lambda could not be estimated. So here what I'd like to show is to try to demystify this idea that lambda cannot be estimated as well as the other parameters. So if you simulate the homogeneous and the heterogeneous versions of this model, so the homogeneous is lambda equal to 1 and heterogeneous is lambda equal to 3. So you get these curves that I show here. First, the top panel is without intervention, and in the middle panel is like an intervention as sketched on the bottom. So the bottom is the coefficient C that multiplies R naught in the model. So at beginning is 1, and then there is a reduction in contacts, and it settles down at the level C1 when the lockdown is implemented. So we simulated those models with C1 equal to 0.3 for illustration, and we estimated the parameters with both homogeneous and heterogeneous versions of the model, and we find strong correlations. With using homogeneous model, we find strong correlations between pairs of parameters. So this could be the issue behind identifiability, which is already present in the homogeneous model. Now we add the coefficient of variation nu, and again, we see correlations as it's shown here. And in order to try to alleviate these correlations, what we propose to do and what we have done is to fit the model to 2 concurrent epidemics in a way that the epidemics, the lockdown starts in different phases of those epidemics. So we basically unlock whatever was correlating the estimation of the coefficient of variation and the effect of lockdown. And here is the result of doing that. So we had initially for a correlation between new and C1, initially we had a correlation about 0.9, 0.8. With one epidemic, only fit into one epidemic, we had a correlation about 0.9. But as we include the other epidemic, the further away the epidemics are, the weaker this correlation becomes. So we end up with we go from a correlation of 0.9 down to a correlation of 0.4, just purely by including by fitting the model simultaneously to two epidemic curves. There could be different regions, for example, England and Scotland. And if we look at what would happen to the correlations between other parameters that have nothing to do with heterogeneity, between R0 and the time at which people start to reduce contacts, then the impact of this strategy is not as strong. So I think this scheme is really effective at allowing the identifiability of this coefficient of variation. So I'd like to thank the authors for their paper and the audience for your attention.
Thank you very much. Our next contributor is Nicholas Irons from the University of Oxford, and I believe he's online.
First, I would like to thank Wood and co-authors for their efforts to raise a discussion about the COVID response, because we are due for a reckoning with our decisions. I would like to focus my discussion on the paper's points about the effectiveness and cost effectiveness of non-pharmaceutical interventions, hereafter NPIs, as these are subjects that I have studied intensively. Aside from the paper by Wood et al., my comments will be based on my recent preprint with Adrian Raftery titled U.S. COVID-19 School Closure Was Not Cost Effective, but Other Measures Were. Regarding the cost effectiveness of interventions, the authors are right to point out the trade-offs incurred by restrictions. However, throughout the text, they neglect mention of the economic disruption caused by the pandemic itself, even in absence of any interventions. This is a significant omission. We know that people voluntarily reduce their own economic activity in response to the threat of the virus. Furthermore, worker absenteeism resulting from viral spread led to necessary closure of businesses and workplaces, with similar considerations for students and teachers in schools. The absence of interventions is not business as usual. That is not the relevant counterfactual. As a result, the authors do not make a fair comparison of COVID and economic outcomes. For example, in the second paragraph of their introduction, they state that taking a conservative 10 trillion pounds of extra borrowing plus lost economic activity as the cost of the interventions gives a cost per life year saved over 10 times the NICE threshold. Sheila has already pointed out that this threshold isn't necessarily one that should be taken as the only number to consider. However, in this quote, Wood and co-authors also attribute all extra borrowing and lost economic activity to interventions, which is not appropriate. In the US, for example, one economic study found that only 60% of the decline in employment could be explained by government policies. And other studies have come to similar conclusions. Furthermore, I would like to point out that taking 10 trillion pounds as the cost of interventions in the UK is not at all conservative by any measure. So in the US, the gross impact of the pandemic, including all health, economic, and social costs incurred by interventions and infection, has been assessed at $16 trillion by multiple sources. This is similar to my own assessment of $5 trillion in the US in 2020 alone. So I don't see how it is reasonable to assume the economic impact of interventions alone, discounting all other health, economic, and social costs of the pandemic overall, would amount to 10 trillion pounds in the United Kingdom. Now turning to the effectiveness of interventions in reducing transmission, which is called into question in section 5 of the paper. I cannot argue with Wood et al.'s analysis of the European response, which is compelling, as I have not analyzed the data myself nor attempted to reproduce their results. However, in my paper with Dr. Raftery, I inferred the effectiveness of US state-level NPI policies in 2020, relying on the Oxford COVID-19 Government Response Tracker database. In our analysis, we made sure to properly account for the time lags between exposure, case confirmation, and death, as Wood et al. Stress here. In estimating the effects of interventions, we also adjusted for the endogenous behavioral response to the fear of infection, also known as the voluntary protective measures. In the end, we found that NPIs were indeed effective in reducing transmission, saving an estimated 860,000 lives in the US in 2020 alone. Notably, our estimates are more conservative than those of prior studies, not accounting for the voluntary response to the fear of infection. We also found that while MPIs were effective, they were not sufficient to reduce R naught below 1 in isolation. This required some combination of NPIs, voluntary response, and acquired immunity. Nevertheless, combining our results with estimates of the costs of interventions from the economics and public health literature, we found that masking, testing, tracing, social distancing orders, and reactive workplace closures were all cost-effective measures, while school closure was not. So what accounts for the differences in our findings? Perhaps due to differences in culture or in timing of COVID's introduction to the country, Americans did not take voluntary protective measures to the same extent prior to the implementation of NPIs. Whatever the explanation, it is clear from the US data that infections did not generally peak prior to the onset of restrictions, as Simon Wood seems to find with his results in Europe. Bear in mind that my study is still a preprint, although it is likely to be published relatively soon. I invite scrutiny from the scientific community, and I hope that for our own sake, we can come to a consensus on this important question. In conclusion, I praise the authors for bringing this discussion to the fore. I agree that a careful review of pandemic decision-making is urgently needed, but I would like to emphasize that such assessments must be based on a rigorous and honest evaluation of the evidence. Analyses that carefully estimate and weigh the benefits and costs of different interventions put us in the best position to make our better policy choices during future outbreaks. Thank you.
Thank you. Well, thank you, Chair. I'm presenting some comments on behalf of Nick Fisher, Noel Cressy, and myself. Over 3 decades ago, when at the Bell Laboratories, John Chambers made an important distinction between what he termed greater statistics and lesser statistics. In our view, the author's article falls in between. The authors are clearly addressing an important issue and their work is exceptionally thorough. However, the focus of the paper is primarily statistical and retrospective in nature. In our view, a broader forward-looking discussion needs to be held as a matter of urgency in preparation for the next pandemic. The need for expeditious action in response to the emergence of COVID-19 was evident at the beginning of 2020. As data scientists with statistical science pedigrees, we were urging the Australian government to start an ongoing national survey to capture data about the progress of the COVID-19 virus in the community. Unlike the UK, we did get supportive interest from some of the major media outlets, and an op-ed was invited and published. Eventually, we submitted a pandemic information management plan to our Department of Prime Minister and Cabinet in August 2020. The plan outlined the various forms of data that should be acquired, the need to convert the data into actionable monitoring information, and the collective skills, knowledge, and know-how required to do this. Consistent with the paper under discussion today, the submission was critical of the undue emphasis on case data and inherent biases that go with it. It also highlighted the importance of understanding the heterogeneity of the people exposed to COVID-19. In fact, an alert government could have developed and implemented such a management plan within the first half of 2020. All that would have been required would have been the chief scientist, or ideally a chief data scientist, taking a strategic view of the situation and having appropriate high-level access to government leaders. That is greater statistics, and many lives would have well been saved with expeditious action. Australia and all forward-looking countries need to establish an Office of the Chief Data Scientist, we believe. The COVID-19 pandemic, the UK Post Office disaster, the Australian robo-debt tragedy, and many others could have been substantially mitigated, if not wholly avoided, with such an office in place to advise on the reliability of data science applications in key policy areas. In current times, the office would also be able to assist the government to manage the risks associated with artificial intelligence, which we view as a subset of data science, although with strong statistical elements. Why do these seemingly obvious and important recommendations keep getting ignored? Clearly, there is a lack of understanding among policymakers of the importance of uncertainty quantification and statistical thinking in determining good policy. A good start to redressing this could be for our profession to communicate in a way that parties at the policy-making table do understand. Thanks for listening, and congratulations to the authors on an important piece of work. It is an invaluable input into planning for the next pandemic.
Thank you.
Good afternoon. My name is Pete Streicher. I'm a research associate at the Department of Philosophy, University of Johannesburg, and my co-author is Alex Broadbent, professor in the Department of Philosophy at Durham University. I'm just seeing if I can put it in presentation mode. Just give me a sec. Anyway, otherwise I'll just continue. So in June 2020, the BBC reported that lockdowns in Europe saved millions of lives, and to be exact, 470,000 lives in the UK. And this was based on a paper by Seth Flaxman from Imperial College, which was published on the same day. Now, recently, the BBC published another article, 5 years on, the countries that never locked down for COVID-19. It listed 8 countries that never locked down, and it was unable to point to any examples where these countries were noticeably worse off compared to neighboring countries. And it stated that in the case of Sweden, voluntary restraints enacted by people in the country appear to have replicated some of the effects of lockdown anyway. So there's no doubt that the confident claims made by the BBC in 2020 were dramatically toned down 5 years later. How did this happen? Now, Simon Wood and his team explained and went into detail how various Imperial College teams most likely misinterpreted death data. According to Wood and his team, fatal infections were already in decline when the hard lockdown was implemented, and a cause must precede an effect. The hard lockdown could therefore not have caused the tide to turn, as the tide had already turned. The hard lockdown could also not have constrained the level of the peak, as the peak preceded the lockdown. Now, I would like to point out how the subsequent Imperial College analyses vindicated the work of Wood et al. Now, I show the Flaxman RT graph on the left. This is from June 2020, and I compare this to the NOC analysis from July 2021 on the right. The Flaxman paper had been cited more than 2,000 times. The NOC paper has been cited only 63 times. Now, there are some key differences. In the Flaxman paper, the effect of initial interventions were hardly detectable, and the effect of the hard lockdown was large. In the NOC paper, RT was already dropping rapidly from 16 March onwards, and in the case of London, it was well below 1 by 23 March. And it was also below 1 in one other region in England. So the left points to a need to exceed a certain threshold, and failing to do so would be equivalent to having done nothing. It creates an all or nothing mindset. The right points more to an 80-20 dynamic, where 20% of the effort could provide 80% of the benefit. Yes, it does point to lockdowns having the largest effect, but it also points to a scenario of diminishing benefits and escalating costs. Now, Simon Wood and his team critiqued the preprint of the NOC paper released on January 2021. I show this graph on the left. During the peer review process, NOC et al. Had to significantly revise this graph, and this is shown on the right. In the graph on the right, RT levels had already dropped below 1 in 2 regions in England by 23 March, the day of the lockdown, and the yellow line shows London. So while there are still some differences between the Wood analysis and the final NOC paper, both point more to an 80-20 scenario, which greatly changes cost-benefit analyses. Only the 80-20 scenario explains why 5 years later we cannot see much difference between countries that locked down and those that did not. And only the 80-20 scenario explains why lifting restrictions, as on Freedom Day, or maintaining light restrictions, as during the Omicron wave, did not result in the large waves as predicted by SAGE SPIN. So in conclusion, the delay in publishing the work of Wood et al. Resulted in the persistence of a major conceptual error, perpetuating an all or nothing mindset. Publishing the work of Wood et al. Earlier would most likely have resulted in Imperial College revising their analyses earlier as well. Both the Wood et al. Analysis and the latest Knock et al. Analysis point to an 80-20 scenario, which greatly changes cost-benefit evaluations of lockdown.
Thank you very much, Peter. Our next presentation is also online. It's from Helmut Kutschenhoff from the University of Munich. Helmut.
Yes, okay. So first of all, I would like to thank the authors for the inspiring paper, which reflects many aspects of our COVID-19 data analysis group at LMU Munich. Following comment: adjustment for excess mortality for demography is essential in our view. In a recent Series A paper, my colleagues De Nicola and Kauermann performed calculations for 22 countries, finding this aspect highly relevant. Interestingly, the results coincide nearly exactly with the results of the paper by Wood et al. For the UK. It was talked much about the lockdowns, so we also found for Germany that the infection curve had reached its peak well before the lockdown in March 2020. The next point is we agree with the criticism of using the case data. In Germany, the situation concerning reliable data was worse, since no random sample like the ONS study has been performed. So things didn't went so bad in the United Kingdom in our view. So we often looked with NY at the data of the UK and argued that the Federal Statistical Office of Germany should perform a survey like the ONS did. The last point is about science communication is difficult in general, but the situation was, of course, as mentioned also in this discussion, worse in the pandemic. So we agree with the authors, they comment on the online world, and this makes things maybe even worse. It's not ideal for this rational, scientific-based politics. However, we as scientists have to find ways for an effective communication in this world. We have to be faster in the dissemination of research results and find appropriate platforms to critically discuss difficult findings as we do it here. Advisory boards should play a key role in a situation like a pandemic. In Germany, our main problem was that statisticians and epidemiologists were not adequately represented in the COVID-19 advisory boards. Thank you very much for your attention.
Thank you very much, Helmut. Our next discussant is Nick Andrews from the Health Security Agency.
Thank you. Yeah, I haven't got any slides. I'm going to read this to try and stick to the 5 minutes. Yeah, this is focusing on the excess mortality because it's something that I've been involved in over the years as well. So yeah, on that section on excess mortality, which was figure 4, I think, the authors use life tables from 2017 to 2019 for the deaths in those years, and the population structure at the start of 2020 to estimate a baseline for expected mortality for 2020 to 2022. And comparing that to the observed deaths gave the figure of 95,000 that we heard about for the UK. And as they point out, that's much higher than the estimates from the ONS, as well as one that was done by Public Health England, actually which then became an OHID on the OHID dashboard. And we were both UKHSA and OHID used to be part of PHE. So that's the connection there. The authors criticise the ONS method is it's based on a baseline on the average mortality. This is the old ONS method from 2015 to 19. So it's just the average with no allowance for an ageing population. And so since there was no age standardisation. And whilst this is a fair criticism, the same doesn't apply, in my opinion, to the OHID method, which also uses 2015 to 2019 for the baseline, but does standardise for age. And further includes a trend for improving life expectancy, because there's a trend used in that as well, which essentially would allow for any improving life expectancy over that period, which is then is in their model extrapolated into the 2020 to 2022. I think the similarity of the OHID and ONS methods is a bit of a coincidence, because the improving life expectancy is sort of cancelling out the ageing population effects. Now, interestingly, an age standardized mortality approach was taken in 2 reports that there weren't referenced that we found produced by the Institute and Faculty of Actuaries in their weekly mortality monitor. There's reports that refer to the same period of 2020 to 2022. And there they, one of them is an international comparison, another one's a weekly mortality monitor. In one report, they just used deaths in 2019 as the comparator, and they get an excess for the period of 151,000. And in the others, they actually use a trend all the way from 2010 to 2019 to predict the 2019 estimates rather than using the actual numbers, because 2019 was a somewhat low year. And then they use that as the comparator, but it still ends up giving, I did a few calculations from their paper to work out around 154,000. So what's the discrepancy with the 95? Why is that happening? I think this is likely to be down to the choice of the particular baseline years. I can see why 3 years were chosen, because it matches, it's convenient to match the next 3 years that we're looking at in the Wood paper. However, that is a particular 3 years. And as far as I can see, there was no allowance within that, for example, for a continued life expectancy improvement. It's debatable whether that would have continued, but I don't think there was any allowance. 2019 was actually a low mortality year, whereas 2017 and 18 were higher by about 4%. And so even within that little bit of data, you could argue there was a trend, although it's only 3 years. But that would sort of average out at 2 to 3% higher than just using, say, 2019, like the Institute of Actuaries. 2 to 3% over 3 years would add to 50,000 deaths. So a large proportion of that discrepancy is easily explained in that way, in my opinion. I did work with OHID in 2020 on their model. I was well aware that small changes to the baseline could really matter. So to remember, January 2015 was a high, and February high period, including that or not in the model would matter. I suspect much of the difference of the 10,000 between OHID and the OHID and the actuaries might be the extrapolation part, because the actuaries didn't do an extrapolation into 2020 to 2022. In summary, estimating excess over such a long period is difficult and probably shouldn't be done. These estimates showing such a wide range of differences is explaining that. I think not assuming the continued life expectancy improvements and the particular years used in the paper are the explanation for these large differences compared to what I would regard, based on the OHID method, as reasonable alternative approaches. Thank you.
Thank you, Nick. Our next contributor is John T. Rougier, who's an independent scientist with affiliations to Imperial College and the University of Bristol. John T.
My thanks to the chair. I'll keep this very brief. Congratulations to the authors for a really fascinating and challenging paper. I just have a couple of comments on their smoking gun figure, figure 10. The figure that shows that UK fatal infections peaked before the first lockdown. I have a couple of points to raise about that figure, informed indeed by the author's own analysis in other parts of the paper. The one thing the authors are very good at is making clear that an infectious epidemic like COVID has got complex heterogeneity and complex time dynamics. In their deconvolution approach, which was used in figure 10, they assume a time invariant, that is fixed, distribution for the number of days between fatal infection and death. And I wondered if, in the light of their own observations about the nature of the infectious pandemic, they had thought about a more general model where they allowed some features of that distribution to change through time. The second one is more of a point than a question. The authors are very clear about the difficulty of interpreting the hospital COVID-related deaths, which they use, of course, in their figure 10. And I wondered if they'd thought about combining two different aspects of their paper. There's the nifty excess mortality or other expected death calculation, which takes account of the age structure, which we've just heard about. I'm not an expert, but it seemed like a good idea to me. And then there's also, of course, the deconvolution approach. Now, I thought that possibly it would be easier to deconvolve excess deaths, right? That is to train their model on total reported deaths. Basically, the expected number of deaths becomes an offset in their additive model, effectively, because that would avoid the problem of attribution of deaths to COVID or not to COVID, which is very difficult in the presence of comorbidities. And it would also maybe give an insight into the wider impact and dynamics of the infection across the country as a whole. Thank you.
Thank you, John T. Our next contributor is Paul Beryl from the University of Cambridge. Paul.
I have far too many slides to get through, so I'd just like to thank everyone and declare the same conflicts of interest as Daniela as earlier. I'm going to just look at the differences between our modelling, which Daniela presented earlier in the forthcoming paper by Joel Kandaya, and the deconvolution results that Simon Good, and look if I can bring the two results together and see what causes the discrepancies. So both analyses are at the heart as a deconvolution. This is the expression from Simon's paper, missing the day of the week effect. But essentially, both models, in their different ways, are different ways of looking at this function f, or how the infection over time is captured. Mechanistic models impose a specific structure on f. And I should just declare that our model also incorporates serology data and a slightly different definition of deaths. But I'm going to ask you to sort of trust me that they don't make a whole lot of difference to what I'm going to present here. So I'm going to look at three components left to investigate: the infection to death distribution, regional stratification, and the degree of smoothing. So if we adopt the time to death distribution that Wood et al. Use, we actually get this is the same figure as Daniela presented, but we get something slightly different here. And we can see that on the left-hand figure is the most wrong model, I suppose, but it's one where the effect is clearer. We actually have a falling R, it can only be due to depletion of susceptibles. And then it starts increasing again immediately prior to the lockdown. And this is because the effect of London, which is leading the way in the number of deaths that are occurring, is waning. And R is a function of is a population of infections average quantity, not a population as a whole average quantity. So this is the waning influence of London. You see that more clearly here if you look at London and another region, which is the northeast. See, the northeast is flat, but London is falling more sharply before the lockdown. So infections are falling in London, but not elsewhere where the R is greater than 1. But there is some falling R value. This allows us, a quick aside, this allows us to calculate some counterfactual deaths that would have occurred if nothing changed other than not having the lockdown, which we know wouldn't happen. So in the case where London, where we think, using Simon's distribution, infection might have been falling, we still get a difference in 3,000 deaths, with a credible interval of about 1,000 to 5,000 were saved or prevented by the lockdown. So next aspect is regional stratification. So here I'm just going to redo Simon's analysis, but looking at the different regions separately. As I said, the first wave is heavily driven by infections in London, whose infectious dynamics may have distorted the national picture. So here is London, and this looks very much like Simon's figure 10, a peak in R before the lockdown, a peak in infections before the lockdown, and R has fallen below 1. We look at the northeast, which is probably, along with the southwest, was probably the slower region. Infections are turning, maybe falling slightly, but the R estimate, according to Simon's methodology, is about, I think it's about 1.4, 1.5 still. So the R is still greater than 1. And then picking another region, sort of, it's more representative of the remaining region, southeast, we get a similar thing. The infections have turned, but they're quite flat, reasonably flat, and the R is still being estimated to be greater than 1. So sort of think about whether the it's appropriate to smooth in this way. Real life is not discontinuous, everything is continuous, but our models are imperfect. So there's things that are missed out that models can't capture. The discontinuities can often be useful to handle. And I was very much interested in the accelerated time model of Wood et al. In the biometrics paper, where it looks like there's a sudden drop immediately before the lockdown. And I think if you presented this to any epidemiologist, they'd say you wouldn't be able to rule out the fact that that drop is actually due to the lockdown rather than something that happened immediately before it. And overall, I think it's difficult to attribute that fall to anything, any particular package or any particular moment in time or any particular input of a package of mitigation measures, even 3 years later, 3 years down the line. So I'll just like to end with the quick results from a simulation study, where our assumed incidence was as estimated by our real-time model, with a log normal delay distribution and a change point in the R value, with consequence effects on incidence. To scale the data to be about the right size, and we're not looking at infectious incidence, we looked at an IFR of about 0.07. And then we fit this deconvolution model of Simon's again to see what we came up with. And the red there is the true underlying incidence, and the grey is the estimated through the deconvolution. And again, we kind of see what we're seeing in each of the regions. We're seeing a peak just before the lockdown in incidence, and an R value that is greater than 1. So lockdown impacts, which they are, because we've sewed them into the model, are in fact smoothed out. So it's a few final remarks. It's necessary to consider regional heterogeneity. There was a very big asynchronous effect across the regions in England. Even with the lockdown, London prevented a significant number of deaths. I'm an epidemiologist, I'm not going to argue about the quality cost of that saving. But it's really difficult, and this is the one I really want to dwell on, it's difficult to conclude anything about the precise timing of infection control from smoothed infection curves. Measures were being introduced at such a rate that it's impossible to apportion declines to any particular one. And just look at the ecological effect of the whole lot. And so the uncertainty about the first lockdown impact, I think, still remains. Thank you.
Thank you. Time's brief. So I'm Professor Kevin Fong. I was former National Clinical Advisor of COVID-19 and Emergency Preparedness, Resilience and Response. We talk here a lot about what would have happened if we hadn't locked down, about things wouldn't have been much worse, that it would have been marginal benefit. I'm here to talk to you about what's in the margins of that for the health service. Sorry, I'm trying to get a slide advance it. Yeah. This is a statement of the obvious, but it was lost on some people during it. All health systems have a finite capacity to cope, after which there is a decompensation that is strictly non-linear. We've seen this during time in major terrorist attacks. I have been on for the 7th of July bombings, the Soho bombing in 1999, major train and transport catastrophes. We cope and then we don't, and then there is a great loss of life because of the decompensation of the system. We talk here in the way that is about the integrated area under the curve. The gradient of that curve is also important. The rate and volume at which you receive patients hurts your system. We had a bad starting point. We have a well below the average for the OECD countries in terms of number of beds per head of population. And unlike Sweden, who are comparable to us, we had many fewer doctors, many fewer nurses, and about 10 to 15% lower spending per head of population than any of the countries that we would aspire to be as a service. At the advent of COVID, we had approximately 3,600 beds in the country. About 85% of those beds were occupied, so we had little or no capacity going in. It's a choice we make about our country. But we talked here in your paper a lot about the first wave and very little about the second, in which we peaked out at 5,702 intensive care cases. That is about 75% really, sorry, is about 80% above our baseline capacity. Now, one says that we expanded our capacity, but beds in healthcare is just a shorthand for the complex socio-technical system that is intensive care. As someone put it to me, we were not running out of furniture. This is an illustration of one of the hardest hit hospitals in the country. And by the way, in my role, I visited all the hardest hit hospitals. There are about 100 acute trusts in the hospital, 100 acute trusts in England. I visited myself personally 45 in my role. My team's put in over 50 visits. 50 out of 100, I think, a statistically significant sample. So this is what happens. The blue bar at the start of March there is a 22-bedded unit. That is what its capacity is. That is what it's staffed to deliver. The red is the ingress of COVID patients. You can see what happens to your blue patients as they come in. They wipe out your ability to conduct business as usual service. This unit stretches its capacity to more than twice its baseline capacity. That means stretching staff and resources. That means reducing space between beds. That means increasing the risk to those patients. What is the consequence of that? Well, Intensive Care National Audit Research Centre have surveyed 130,000 ICU admissions across 207 hospitals, finding that unprecedented ICU strain leads to a significantly higher hospital mortality. That is what lies in the risk of strain in these systems. Look at the figure below, and I can give you an impression for this. During the attack on 7th of July 2005, 21 critical care admissions across London in 5 teaching hospitals stretched the resources of those units quite thoroughly, 21. And if you look at the peaks here, you're getting about 15 critically injured patients received not by 5 teaching hospitals, but by 1 teaching hospital per day. The registrar from this hospital put it to me that it was like a terrorist attack every day and we didn't know when the attacks were going to stop. And that's not, by those numbers, a hyperbolic statement. A measure of the stress in the system is the number of transfers we're undertaking. In the year before COVID, nationally we transferred 68 patients to create capacity in units for overrun. In the year following December 2020, we conducted 2,152. I shall move on, but you can see this graph. It's not just quality, it's not just quantity, it is the quality of what you're dealing with. This is the death rate amongst the patients that we brought in. This was the hospital that I described. In 1 month, the hospital saw 354 deaths, of which a large fraction happened in intensive care. For every patient that they were admitting in that month, about 1 in every 2 of them died. Please imagine what it is like to be on a unit to watch 1 in every 2 of the patients that you see die. During the full scan of COVID, about 1 in every 3rd patient died on our units. This has an impact not just on the patients who I've told you are at greater risk of dying, but it also has an impact on the staff. Can you measure that? Yes, you can. We use the same tools that your GP would use to measure your depression, rates of anxiety, harmful use of alcohol, and importantly, your post-traumatic stress rates. With the PCL6 measure, a registered and normalized tool for this, we found that during the January peak, again, which is not much discussed in your paper, that the rate of probable PTSD amongst doctors and nurses was about 46.5%. Prior to the publication of this paper, the highest rate of probable PTSD in any population surveyed was British military veterans deployed in a combat role in Afghanistan. It was 17%. There is an aftermath for this. One of your success criteria for COVID should be that you have a functional health service in the aftermath of it. In the year 2022, the greatest number of nurses left the service in the history of the NHS by proportion of nurses and by total number and relative. We now have a health service that is younger and less experienced than ever it was before, which costs us money by recruitment and retention and training. It hurts our patients because they're less experienced and there's fewer of them. And we have a sickness rate that's 1% above the pre-pandemic baseline across staff of 1.5 million people. There's substantial loss of staff. And we have a 10 to 15% loss compared with pre-hospital of willingness to take on discretionary effort. So we hurt our service. And this is what lies in the margins. It was hard. Don't ever let anyone tell you it wasn't hard. This is my last point. That middle photo is a mother and daughter team going on to shift on Christmas Day 2020, when there was no access to vaccinations routinely for healthcare staff. You can see what that is. You can see what this did to our service. So thank you for this discussion. Thank you for bringing this to light for debate. I think you do ignore very heavily what is in the margins of a little bit worse, not much better for the health service. Thank you.
Thank you, Kevin. So that concludes the people who pre-registered. I'm afraid, given the time, we're going to have to move on. We did get 15 written contributions. I'd like to remind people that they can still submit written contributions. Believe we can submit written contributions up till the 9th of May. And so please do submit up to 400 words as a contribution to the paper. So with that, I'd like to give Simon the opportunity to reply if he wishes to. He can have up to 10 minutes, although please don't feel like you have to. You will get the final reply in the journal in writing. And you can, of course, consider all these points and all the other points that are that will be discussed in the written contributions later on. Simon.
Okay, sorry. So Notre here wanted to register and speak and then didn't get the chance. So I was just going to give her a few minutes of our response time to say something. I also wanted to get some slides up for.
Thank you, Simon. I'm sorry for messing up. Yes, I'll just very quickly. First of all, thank you, Kevin, for that. Shunetra Gupta from the University of Oxford. So yes, thank you for that, illustration of the dire state of our national health system. As you can see, there's a lot of uncertainty. The word uncertainty kept cropping up. It seems that people are now agreed to an extent that that the peak of the pandemic perhaps had been reached before the lockdowns happened, but there's still disagreement. Let's assume it had happened. What brought it down? There's disagreement there. We've heard about heterogeneity. We've heard about behavior change. Personally, I think the whole thing can be explained with a simple SIRS model. Immunity to COVID does not last forever, like measles, which is an SIR, with seasonality. And I don't think you can analyze any of these things with confidence without bringing seasonality into the mix. Okay, so what are we talking about here? We're talking about a scenario where what happened during the pandemic, or what was going to happen, was not something you could determine with the help of a mathematical model. There were various scenarios that were all possible under very simple assumptions concerning loss of immunity, seasonality, heterogeneity in the population, voluntary behavior change, etc., etc. And indeed, of course, the NPIs. Now we know that the NPIs did very little to stop COVID, but that's not to say it didn't have any effect. It had a very strong effect on endemic diseases, such as flu. They disappeared, and that's also very simple, basic epidemiology 101. But we didn't know that at that point. We didn't know which of these things was really how the epidemic was going to unfold. What we did know, though, is that lockdowns would cause enormous harm, enormous damage. So under those circumstances, it was incumbent upon us to come up with a policy which I think, which some of us did suggest that the best way to go about this would be to introduce a system of individual risk reduction or focus protection for those who are vulnerable, which was already known. That was already known at that time. So fundamentally, I think where we are now is a place where we know what the schedule of certainties and uncertainties are a bit better, but not in sharp detail. And what we really need are debates like this. It's absolutely essential that people don't shy away from voicing their different opinions and different perspectives and maintain a healthy, respectful interaction that can take us forward so we're better prepared for the next pandemic. And thank you, Simon, for putting out this exceptional paper.
So whilst we're doing that, we finished there with a very powerful and emotional discussion of the situation in the health service. And I think we can all appreciate what was going on in the health service. But all the people sitting in this room are from the Zoom classes. I come from a family that wasn't from the Zoom classes originally, right? At 10 years old, I remember my uncle's funeral. Well, I stood next to my 10-year-old cousin, who was the same age as me. Now, I can't be certain that if my uncle had been as well off as we were, that he would have died early, but he had 4 kids. He got ill. He had to go back to work because they couldn't afford it. He was dead at 40 something, leaving 4 kids. Right? Those are the people in those life loss statistics that I told you about. Right? That's an emotional thing. I wasn't going to do that, but we had an emotional thing about the state of the health service, and emotions are involved here. Politics is involved here. So I'll get back to the less emotional stuff. Sorry, I have difficulty with mine. Okay, so I just want a quick thing. 10 to the 12 is 1 trillion, not 10 trillion. There wasn't 10 trillion of taken on by the UK government. We didn't say that. On the basis of, yes, of course, COVID would have cost with lesser mitigations. Our point is it might have cost less. So again, everybody complains about comparisons with Sweden. It's right-wing talking points, although I'm a member of the Labour Party and knocked on doors for Corbyn. But look at UK government debt, right, and Swedish government debt, right? I mean, you know, there is some sort of a counterfactual there. Not perfect. Right, so I'm mostly not going to reply to things immediately because quick reactions are, I think, damaging, as we saw, I think, repeatedly over COVID. There was a quick reaction on Twitter that wasn't necessarily a good thing, and you're combining a whole load of very quick reactions that doesn't give you a considered reaction, right? I think this is a big deal. So we'll mostly consider what people have said, which has all been quite interesting. However, I did want to say something about smoothing assumption, because actually we've done some work since then. So there's this thing about incidence and smoothing. That kind of bothered me a bit, and it's sort of come up repeatedly. So I just removed it from the analysis method. We've come up with a method which is under revision for biometrics at the moment, which involves no smoothing at all. So those that are first wave deaths in the UK, the black dots that we've seen before, lockdown dashed. The red curve simply moves everybody back by a random draw from the infection to death distribution. Obviously not an appropriate way of reconstructing incidence. And you can see that if we move them all forward by another random draw, that gives you the set of grey curves there. It doesn't match, obviously it's not going to. But what we can do is just simply resample to correct. We can produce a very simple resampling method that doesn't make smoothing assumptions, that simply says, okay, let's move anybody's day of death by a day of infection by a day or two. Does that improve the fit? And let's clone people. Does that include the fit, right? And you just repeat that process. You don't make a smoothing assumption. And we can do that. And so here's that method applied to basically the data up until the 14th of April 2020. And the reconstruction of instance that we get by doing that. There it is by the 21st of April. There it is by the 28th of April. And again, I simply want to make the point, you can debate whether or not we should have locked down. And I think that's a completely legitimate debate. I think the difficulty is in then what happened afterwards, whether you should have stayed locked down, right? It's a matter of degree. Right? Everything's a matter of degree. It's not, they were not binary absolutes here. And then that's incidence without smoothing the first, for the entire first wave. You can also construct a hypothesis test this way of whether exponential increase up to lockdown followed by decrease is plausible, right? So on the right, we've got exponential increase followed by a crash that will exactly match the observed data. But I don't have time to describe it exactly now. It'll be in the preprint. But the p-value is about 10 to the minus 6 for that one. I'll perhaps stop there. We're over time anyway. Thank you.
Thanks to everybody for all their contributions today. It's been a really, really interesting discussion meeting. I hope both the authors and all the discussants feel the same way. I really would encourage everybody to contribute in a written form. I think there's an awful lot here, and I think it would be really, really valuable for everybody to commit that to writing so that it can be recorded in the journal. The next discussion meeting is on the 10th of June and will be held at Imperial College London. It will feature another COVID paper, new tools for network time series analysis with the application to COVID-19 hospitalizations by Nason et al. There's full details of all the upcoming discussion meetings on the RSS website and will be announced in members' newsletters and online and on social media. If you're not a member of the RSS, I really would like to encourage you to become one. Tom?
quite thoughtful, detailed contributions and hit that quite hard given the content. So I don't think everyone here would be quite happy to read, 50 to 100% more than that their contribution if it sort of deepens our understanding.
Simon, yeah, go on. That's excellent.
I'm not going to tell you how much a bit is, but if it's several thousand words, then no. I put something in last night and got bounced, but it came in about 600. But it used to make a point about 600. Yeah.
About 400, please. Thank you all very much. If you'd like to receive, I was going to say, if you'd like to become a member, please become a member, and if you're not already. If you'd like to receive an invitation to future discussion meetings, please email journal@rss.org.uk, and we'll make sure you add you to the discussion mailing list. There is a reception downstairs. Please follow staff to the Wigmore suite, either down the stairs or, of course, you can take the lift. And with that, I'd like to thank everybody again.